This is Carl from Bristol University, and I'll just let you take
And let me get on with things. Okay, well, morning. There's always going to be people dropping off during the week, and it's because people realize the beauty of Sheffield beer. Which is a good thing, So I'm going to start off by being polite and introduce myself. So I live in Bristol, that's here, which is in the southwest of England. And that's where I live. And this is what I do. So I ride bikes. That's my favorite pastime in the world. This is a Colnaglo Master Extra Light, built in Italy. Straight top tube, stainless steel straight fork, Campagnolo super record, completely Italian. This is my dream. I will never ever, if I stay in a university, be able to own one of those bikes. But, so if you then live in Bristol, you have lots of opportunities. So you can cycle and you can go across the river and you can get into Wales. Wales is really nice. They have lots of sheep, which some people say they do indecent things to. I haven't seen that. If you end up here, you get to a place called Port Talbot, where there's an old steelwork, which is very nice. And one of the things is when you cycle a lot, you want to eat a lot. And there's a cafe here, which I usually stop in and eat a lot. And then another tour you can do is you can go down south here. You can get to Exmoor. This is really, really pretty. The steepest hill in the UK is here. It has 26.2% gradient. It's fantastic to cycle over. So one time I was here in Lynmouth, and I looked across the sea, across the British Channel, and I saw this. So I looked across, now hopefully you can see it is dark enough, and I saw the steelwork. And that kind of surprised me a little bit. So then I went home, and I made a measurement. So I measured the distance from Lynmouth to Port Talbot, and I realized that was 50 kilometers. And then I kept doing some geometry, and I thought, okay, so the distance to the horizon from that point with the bending of the Earth should be 6.2 kilometers. That means that the hidden height on that side should be 125.6 meters. This is a little bit surprising. So I came back and looked at this image. And then I went to a website called tallbuildings.org, where they have the measurement of this. This is the chimney. It's 135 meters. It's substantially taller than these buildings. Still, I was able to see them all. This was really confusing, and I didn't know what to do with myself. So as a machine learner, I then tried to build a model that could explain this data. And now I'm here today to come out in front of all of you because I've realized the Earth is flat. Because this model of this data explains this absolutely perfectly. It also explains why I can, from that Lynmouth point, see the lighthouse in Weston-super-Mare, which is about this tall. Fantastic. It's really simple. And also what it does, it made me realize now clearly why there are no dinosaurs in Exmoor. Because at one point in time, a meteor hit this plate and it started spinning and the dinosaurs fell off, right? It's a really, really simple explanation that we flat earthers like to use to explain why dinosaurs don't exist. Great. So apparently, this was my introduction. Apparently, according to Javier, a good talk in statistics should have a joke, a theorem, and the theorem should not be the joke. This was not my joke, because what I've used to explain to you is the no free lunch theorem, right? No one can argue with my explanation of the data points that I just saw. They're absolutely correct. They explain my data. I could explain loads of different observations there, right? No one can argue with that. And this is what we often call the no free lunch. And we say this, and it's often mentioned in your first lecture in machine learning, but still it kind of always seems to get forgotten. Because in the end, we still read papers, very recently in Nature, that really explains machine learning as a black box that can do anything without human input and without any assumptions. It's always fascinating when you write papers and people seem to be saying a benefit in removing assumptions. It's the total opposite, right? The benefit is making assumptions. That's why we're here, right? So now, let's now be a little bit more serious about this. So if we now think what machine learning actually is. So machine learning can be considered as inductive inference or inductive reasoning. And one way of thinking about this is just this nice quote. In inductive inference, we go from the specific to the general. We make many observations, discern a pattern, make a generalization, and infer an explanation or a theory. The important thing with this, which is again no free lunch, is that this can never be right or wrong. You cannot prove this. You prove things by deductive reasoning. That's why mathematicians deal with this thing here of inductive inference. You can always, if the sample size is infinite, come up with any possible explanation, any possible theory that explains this. So then people have actually looked at this, right? Looked at learning theory. And I don't know a whole lot about it, but I thought it was a nice thing to think about after having talked about GPs for 2 days. So let's think about machine learning is very abstractly. We're generally looking for some form of function that's supposed to do something. It's either supposed to map from something to something else, right? So we have some space of functions. This is where the solutions that I'm interested in searching in. I can make this big or small and so forth. Then I have some form of learning algorithm, which is going to search in this space of functions, right? Then I have some form of data set, S. Here I've said tuples of x and y's. And hopefully, this S is a sample from a true data distribution. And then I have some form of loss function, some form of measure that says how well I'm doing. So here, I'm going to say this is a mapping that algorithm A has learned from the functions f when it took the data s. And this here is what I'm looking for, right? And if you read statistical learning theory, what they say is that what we're looking for, what we're really interested in machine learning, is finding or minimizing the expectation, the expected loss, right? So I take the expectation over all the true data distribution over the loss to this data, right? This is my aim. This is what we do. Now, the tricky thing here, and why this is hard, is that I don't have access to P, right? I don't know P. Right? If I knew P, well, job done, right? If I could parameterize the data, well, that's all what we're trying to do. So what people generally do is you do this empirically. So now you take some data set and you take an empirical estimate of this. So now the interesting thing comes, and this is more specifically what the no free lunch is. I can come up with any combination of loss function algorithm and this data set. They give you an arbitrary value on this, right? Take the example of my flat earth theory. It's great, right? It has like 0 error on the observations that I had of that steel plant and some other things as well. But hopefully it's wrong, right? There's a hell of a lot of things that simply it doesn't explain particularly well, right? For example, I flew to America not too long ago. That wouldn't work, I think. They have certain theories about this flat earthers. I recommend going to their forums. It's really fun. So now, one thing that I wanted to contrast why I really picked this up was a bit of motivation to Gaussian processes. So if we look at this object here, the loss function, often we can kind of agree on. The interesting thing is the algorithm and the function. So neural networks are very popular at the moment. What neural networks does, so in order to make anything, we mean to make assumptions about this, right? That's like, I didn't say that, hopefully it was obvious. And in neural networks, what you often do is you make very few assumptions about f, you specify a class of functions, but you make massive assumptions about how you search that space of functions. So for example, there's no way these algorithms would work without stochastic gradient descent. Stochastic gradient descent is a really, really good way of not ending up in your global minima if your energy function looks like this, right? People don't want to do that because often these models have very trivial solutions. And you want to make sure that your algorithm doesn't find them. What we do instead here is that we make very, very clear and strong assumptions about f. We try to say, I'm going to put a very strong structure on the space of functions, and then hopefully that is what's going to give me structure to find a solution, right? To me, I find that much, much more natural way of thinking, right? I put structure on what I'm looking for, rather to say, you know what? I'm going to put on shades, and I'm going to not look with this eye, and then I'm going to find exactly what I want, right? So that's kind of a little bit of introduction to that. Cool. So where do we go? So what am I going to talk about today? So first, one of the benefits I find with the Gaussian process summer school is that lots of people keep saying exactly the same things over and over again. And that's really useful. And I've been here for many, many years. And I realize I see people giving the same talks, and I realize they're slightly different. Neil's talk on the Gaussian distribution, he said this himself, it becomes shorter and shorter every year because he realizes more and more things that he wants to say. And if someone that's thought about Gaussians for that long start realizing new things about the Gaussian distribution, well, then we need to be really careful, right? So what I'm going to try to do is that I'm going to give my view on what GPs are, again, which is a slightly different. Then I'm going to talk about unsupervised learning, and you're going to realize very quickly it's dead easy. Unsupervised learning is the easiest thing there is. It's much easier than supervised learning because anything's correct, right? It is, right? Unsupervised learning, they give you some data, give it back to them, right? Perfect, it's unsupervised learning, right? So the tricky thing with unsupervised learning is if we want something specific. And then what we need to do is inference. Formulating the problem is really, really simple. It's going to take me one slide. Doing inference is really hard. So I'm going to talk about variational Bayes again, but I'm going to talk about it slightly differently from James, because the way James explained it, which I think was really nice and saved me a lot of work, I'm going to talk about the assumptions that we actually make by doing variational Bayes in GPs, because it's actually very, very peculiar, and it has some very, very interesting intuitions. So hopefully we'll follow those. And then I will, in the end, go super quickly, and I'll show some crazy models, right? What you can do with this, which really, when we have this framework, is like, right, we're nearly like TensorFlow crazy. We can use like, I'll just stuck this to here, to here, to here, to here, and then something happens, right? So that's the aim. So then we're going to talk about learning, and we're going to get to Gaussian processes. So learning, if you haven't read it yet, read Judea Pearl's book that came out, The Book of Why, came out this year. He says this thing, machine learning is nothing but curve fitting, but it's amazing what you can do by fitting curves. So then let's think about fitting curves, right? So this is my intuition of how GPs works. So we need to think about fitting curves. So that means I need to think about this, right? This thing here has curves in it. If I draw one-dimensional curves, they're going to end up on this plane. So that's kind of hard to think about. It's especially hard to think about how the hell do I parameterize that. I really now want a distribution that says, oh, that allows me to tune and say, I like certain curves more than I like others. How do I even come up with that? Well, one thing that you can think about, you can start reducing this problem by thinking what's true for every curve. Well, if I look at this line, this is one line, 1 point in x. This slice here, what I know is true for every curve is that every curve, every function, has to pass this line once and only once. If it passes 2, it's no longer a function. If it doesn't pass us, it's a function that isn't defined over the whole space, right? Okay? So that we know is true. So let's now, instead of thinking about the space of functions, think about the space of intersections of a function with this. Well, that's much easier, right? It's really easy, actually. So what we're doing now, when we think about Gaussian processes, is we say, great, that's Gaussian. We say that this here, the intersection of the function and this line is Gaussian. Now, if I said that at 3, I never said 3, it was just a specific place. So clearly, if I said that at 3, that must be true at -1 as well, right? Like the same argument would hold. And if it's true there, is quite possibly true absolutely everywhere, right? So now, what we can think of, I've now taken this discrete but very, very many slices. Now this goes towards infinity, and the way I would write this variance of this is now just a constant function, right? That constant function is the diagonal in your covariance matrix. So now, cool. Now the next thing, yeah, that constant function will now give you this, right? Your infinite Gaussian, your Gaussian process. So now this isn't particularly interesting because there's the main thing of functions we haven't captured. So if I say now, we come back to our slices at -1 and 3, if I know that at -1, the value is 2, does that have any information? Oh, actually, I know it's 2, but a little bit of noise, right? Let's do that. We should always be a little bit uncertain. So if I know this here, does that give me any information about this? Well, either we say, you know what? This here says nothing about this point, so it's just my belief here doesn't change at all, right? So it's back to the same thing. Or the other way would be saying, well, it says everything, right? If I know this, I know that. So it's exactly the same belief. I just move it. Or probably what we have is somewhere in between, right? It's somewhere in between here. And this here, obviously, the variance of this one is the off diagonal in a Gaussian, right? So you parameterize this with your covariance function, you get your off diagonal. Another way of seeing this is that as soon as I take 2 slices of this, I take 2 lines, I get a 2-dimensional Gaussian. Here, if I have a 2-dimensional Gaussian, I know the value is 1 on like the point that's x1, so the y value of that is 1. I take the conditional distribution, well, it's pretty much 1 on the other. If it's 0, clearly it's independent. That one doesn't say anything about the marginal is the same the whole time. Cool. So that's my engineering-y, hand-wavy notion of what a Gaussian process is. Great. And that then allows us to do all these funky, crazy things, and sampling and getting functions and all sorts of funky stuff, right? So, and obviously, the really cool things, we can do base rule in closed form. So now then, the meat of the talk, unsupervised learning. So what we've seen so far is this. People have said, I'm going to give you some x values. These you know. I think in every case you've seen, they've always been assumed to have no noise on them to begin with. And you've said, now, they are related to a y value. And what I'm going to do is that I'm going to say there's a Gaussian process, there's a prior on this relationship, and you have this, right? So this here is not the random variable. It's just known, it's something that indexes this graphical model, right? So what we've been looking at is this object here. Or really, if you're a proper statistician, which I think people in machine learning should try and be more, including me, so we shouldn't even write the x there, right? Because the x here it's not the variable, it's just something that indexes, right? We're terribly sloppy with this, me included, as you can see. What we are going to do now is that we're going to look at this object. So now I don't know what this is, right? So I only have some observed data that I'm going to say have been generated by a function, but I don't know from which inputs, right? That's the idea. That's unsupervised learning for you. So now this thing here becomes latent. So what we want to do in terms of learning is now integrate out this, and end up with this object here, right? Integrate out this as well if these are your kernel parameters. In this one here, we just integrated out this one, right? Yeah?
What is capital D?
Capital D. Oh, yeah, sorry. If you're not familiar with graphical models, so what this thing does here, D, is basically it says that you have your likelihood is basically per dimension. You predict, if you do multi-dimensional stuff, what you normally do is you predict each dimension and you just multiply them together, right? So your likelihood function will be a factor over the dimensions. So that product will actually go over n and d, right? So that's normally how. So this is called a plate notation. So the only way the way you see this is that you take I of these and you have a multiplication over them outside, and that gives you YF, right? Yeah, if this makes sense. Good question. Keep asking me if I.
Is it now the number of the dimensions?
The dimensions of the output. No, then it would be n. So the number of dimensions is what. So if this is a 1D case, you wouldn't have this plate, right? Yeah. Okay. So one way of thinking about this, we've seen all these. You saw my introduction to GPs now. So let's think about unsupervised learning. So does everyone know what an abacus is? Right? It's this thing that we count with, that you have small balls that sits on a metal thing, and then you could move them around to count, right? That's unsupervised learning. So the way you have to think about it is, I've been given y values, but they have no corresponding x. Each of these y values now sits on a metal thing, and I now should slide them out and give them an x value, right? That's unsupervised learning. It becomes more interesting when this has a much higher dimensionality than this, but it becomes really hard to draw that. So we have to do this in 1D, yeah? So, cool, I can do this. So I tried this, cool. I've now moved these out a little bit, and I've also connected them up like some fake function. Yeah, well, that's one way. This is another one. This is a third one. And I went one too far. Oh, well. So if you look at these, just instinctively, could you say that you would be able to have a preference over these? To say that actually, this one here looks much more unlikely than this one there. Maybe, right? You could have a belief that, for example, saying, I believe in a solution that gives me a very slow varying thing, right? This would be much more slow varying, if you wanted, than the thing that I put them like this, right? So that's exactly what a GP does, right? So what we're going to do in unsupervised learning with GPs is that basically take f, the prior over the function, and say, if I give a function, the way that associates the x values is the way I'm going to pick the x values. Does that make sense? Right? That's the way we're going to do it. So I'm going to give you some examples here where I've drawn. Another way to think about it is to think like this. If I have my GP prior and I take shed loads of samples from it, now I place these points on my abacus like this, and I remove all the samples that didn't go through them. The simplest thing would be the one that has the most functions going through it, according to your GP prior, right? According to your preference. There's nothing that's right or wrong here, right? You have to have a preference. If you don't have a belief in what you're looking for, anything's possible, right? Absolutely anything, yeah? So, cool thing, what I do here, this value here is unnormalized, but this is actually the likelihood over these points coming from this GP prior, and I've drawn a couple of samples. So the interesting thing is here, this value I want to make as small as possible. So here, the interesting thing is that because these points are very, very close to each other, the function had to like shoot up there, so it becomes very unlikely. This one here, now they're much more nicely wider spread, so this one, it likes a lot more, right? You could argue that you prefer this one more or not, but this is now what your GP prior controls. Rather than the function, it controls the x positions. Here you had something else. This was exactly the same as this. And here I had something that was basically the same thing as before. Something was shooting down a lot like this, right? And it doesn't like that because these are too close. Okay, great, fantastic. So say that we have smoothness as a prior. So we like things that are smoothly varying. I hope you agree with me that this kind of makes sense. But there's one thing I can do to make the function really, really smooth, right? I have the whole infinite axis to work with. I can just push these points as far away as I want, and that is going to be a very, very tiny thing. I can make a line out of anything, right? I can just move it as much as I want, right? So that doesn't really work either, right? Really annoying. So what we need is also a preference over this. And we need to mix these two things together. And that's when it becomes hairy. So another way of thinking about this, I often think about being Bayesian, is that you have to have everything in balance, right? So often, when you formulate models, you realize you formulate one preference, but because I haven't fully constrained my model, because I haven't fully placed priors over every variable and integrated them out, the model often ends up being, oh, cool, if you tell me that, I can go here. And now I avoid dealing with all these preferences and I do something really, really silly. So often we need to come up with ways of trying to find a balance, right? So cool, let's think of balance. So let's just, for example, say that we put a Gaussian blob on the latent space. The only thing that's going to do is that you want the latent space to be small, right? The ideal position is I put everything in one point at the mean. Well, then the GP is going to say, I don't like this at all. So now you have this struggle. You have this balance between the Gaussian blob saying, oh, you should be kind of small, and the GP saying, I want you to be kind of smooth, right? That's good. That's balance. So great. So what we want, P of F, that makes sense, and I want P of X that makes sense, that describes somehow my assumptions about these two things. So great, now this is super easy, right? Because we're Bayesian and we've been taught all these things, so the only thing I need to do is that I write up all this, my likelihood, my GP prior, my prior over the latent space, I integrate out all these, and we're happy, happy, joy, joy. Now, let's just think about this. P of F is a Gaussian where it has a covariance matrix. The covariance matrix sits somewhere in this distribution inside the exponent. The covariance matrix itself is an inverse. Each element of that inverse itself comes from a function which is an exponential where the x sits up in that exponential as a square. And that's just that bit. Now I add this bit, which is another exponential where f now sits up in this, right? Now, think about this. You are trying to push your assumption of x down to y, right? The whole way. What is my assumption of x? How does it relate to the data? Getting this x through this nonlinearity, through this, is simply really, really hard. Try and write that up. You're just going to get very, very, very stuck. This is intractable. What it actually is, it's a non-elementary integral. It has often these things, and I believe this has, infinitely many terms. So you simply can't write it up. And you can kind of see that it's infinitely differentiable, so you can't do a Taylor expansion or anything. This is just not tractable. And that's why we need to do approximations on this, right? So another way was my only Laplace quote for today, was that apparently Simon Laplace said nature laughs at the difficulties of integration. So another way of seeing that being Bayesian requires you to be in balance is not that cute seesaw picture, but actually seeing this one. This is a lot about how it is being Bayesian. You need to have the world in balance. We're looking for the truth. So if you're torturing someone like this, you want to stretch them, but importantly, you need to stretch them evenly from each side, right? And the integration part is the really, really painful thing that happens to this person, but in the end, truth will come out, right? So, and that's what we call the marginal likelihood. Great. So that's why most of the work, I hope you believe me now, that cool, unsupervised learning seems to be trivial, right? It's dead easy. I have this awesomely cool tool that are GPs. The thing is, I really don't know, I need to add P of X, and I can't do this analytically. So the whole issue is inference, right? So that's what we're going to talk about for quite a long bit now. But before that, I'm going to say, before people started thinking about inference, this was when I did my PhD. Before that, there's certain things in machine learning which, when you hear about them, you think that that's absolutely incredibly obvious. And those are the really, really brilliant discoveries, right? When you hear them, you'll be like, oh, I should have really thought of that. And one thing is just to say, well, actually, can't integrate out x. I'm just going to do maximum likelihood. I'm just going to see x as a parameter, and I'm just going to take derivatives, boom. So I'm just basically doing GP regression, but x is now parameters. Clearly, this can't work. It's ridiculous, right? It's absolutely ridiculous. You have as many parameters, x, as you got y. Blah. Can't happen. Well, it can. And it actually works fantastically well. So Neil did this 2002 or something, and this is what's called the GPLVM. So now, the thing, this is your objective for doing GP regression. Now, you only need to be able to take derivative in terms of x of these things. Boom. And it kind of works. It's really, really cool. And I'm going to show a very small, oh, lots of papers on this. I'm going to show a very short demo. Oh, now this moved to Dunk. And I need to do this. This is from my colleague Neil in Bath, who's very, very good at making very, very pretty things. So what we have here is that we have y, which is this letter, which is a contour of a letter, incredibly high dimensional. It's probably 1,000 or so dimensions. Then we say, I'm going to want a two-dimensional x, and I'm going to put the GP prior with an RBF kernel from here to here, right? End. And now we just try and optimize this flow. What happens now is that now I can pick any x, and it should generate any y, right? These data points here are the observed things. This data set here is different fonts. So this is letter A, and each dot is a different font of letter A. So what you get now, if this works, is you can move around here, and you can generate different fonts. This font there doesn't exist, right? There's no training data there. This kind of still looks like a letter. And if we actually look at the behavior of this thing, it seems to have captured some form of serifness going this way, and what is it going this way? But to be completely fair, this I think is when we start becoming neural network people and start imagining things, right? It's captured something, right? But it's really cool, right? So this is you saying this really, really simple thing actually does work. So now let's move. Yes?
So when you say you're doing maximum likelihood, is that for some y you're doing an optimization over to find an x?
Yes, exactly. So basically you take all the y's that you have, and then you say, cool, I'm going to put up a GP regression problem. The only thing is I don't know the x, right? So I write this up. Your GP regression looks exactly like this, right? We've seen this thing before, right? If you marginalize out f, you're going to get something that looks like this. Forget about this one here. It's actually not particularly important. So now you've got this. In your case, what you did before, you had one parameter in here. That was the length scale and the variance or something, your kernel parameters. Now, this covariance matrix has also x as parameters. And you just take derivatives of them.
And then you find x, but then you showed this.
Yeah, but you also find f, right? You also find the covariance parameters, and you also have f.
So why, if you want to find the covariance parameters, because that was the animation that you showed us?
No. It was taking an x on that space, pushing it through the GP that I've learned, and getting y.
Which is defined by the parameters that you found.
Yeah, exactly. So in the end, what you do, you optimize them as well.
So why would we, my question maybe is, why would we want to find x?
Oh, isn't that great? I just gave you a two-dimensional representation of a 1,000-dimensional object. Unsupervised learning, right? Yep. That's the whole point. As I said, no, you're really good, right? Because this, you're just showing clearly how easy unsupervised learning is. Because there's no truth to it, right? It's so clear that you have to make an assumption. Like, I can give you anything back. As long as I enumerate your data set, it's an explanation, right? So generally, people pay you lots of money to do it. Just hand them back the data set. It is unsupervised learning, right? In a weird way. I've given you an identity function. Yeah? Cool. Excellent. So there was lots of papers on this. I spent my whole PhD trying to do this. Main thing was to try and initialize this horrible thing. Maximum likelihood it simply doesn't work. And then I thankfully managed to finish my PhD before these very clever people came along and said, actually, let's just be Bayesian about this. Let's do variational inference and everything works. And all the stuff I spent 3-4 years doing was totally irrelevant, which was great. So there's 2 really, really important papers, I think, by Michalis Tessias and Neil from 9 and 10. They're really, really hard to digest. And one of the reasons why they're hard to digest is the notation is different in the 2 papers, which is really, really annoying. But that's how it is. And also in the first paper, the most interesting thing is in a footnote. So it's really hard to digest, and it's just because Michalis is a little bit more clever than I am, quite substantially more. So now, the problem with ML estimation is I don't know how to initialize X. It's a gradient-based optimization, shed loads of parameters, it's going to end up in local minima. I don't know how big X is. Like, what's the dimensionality? Why the hell did I put 2? Right? It could be 10, 4, 9. Shouldn't I learn that? And the big problem is my assumptions on the latent space does not reach the data. My prior on the latent space, if I put a prior, as you saw, it just becomes like a regularizer. It has no connection to the data at all. It doesn't work like a prior. So what we need to do is do approximate integration and do variational base. This is what works. So now I'm going to very much run out of time, but I'm going to go through my view of variational base, and then, which is slightly different than James, and then I'm going to explain what it does with GPs. So machine learning, to me, is about trying to find this object. The marginal likelihood, P of y, the evidence, that's the object that we want to maximize somehow. If we make the assumption that the sample data I've seen is well representing the distribution of the data. This is the object that I want, okay? It's the object that I often can't reach. So now, if I say want to optimize this, it doesn't matter if I take the log of it or not, right? It's just going to be the same thing. So I'm going to look at the log of P of y. Now, I can write P of y as just a joint distribution where I marginalized out x, right? Fine. Now, what I can do is that this joint distribution, I can use the product rule and write however way I want, right? The way I'm going to write it now is that I'm going to write it as the posterior distribution, so P of x given y, x, let's say x is latent in this case. Well, it is. P of x given y times P of y dx. Okay? This is absolutely fine. I've just done the product rule. Now, I'm going to do one thing that's a little bit weird, but it's nothing strange. So what I'm going to do is that I'm going to put a distribution over x that I call q, that I just put q, q. Boom, I've done nothing. This is still an equality. Okay? Now, we're going to do something interesting. So now, and this, I think, is very important. So this here is what is very easy to think about. If I take 2 points here, or if I take this point and this point, any point in between here, if this is a convex function, it's going to lie above the function, right? That's the definition of a convex function, right? So that's great. Now, what that means is that if I have a convex function, and if I take the expectation of that, that's always going to be above, because the expectation is basically moving along here. Or if I take the function of the expectation, which is first picking something here and then taking the function of it, right? Does that make sense? Yeah? It's just a convex function. So I have this rule with expectations. So what I can do is if I have a function of an integral here of x, I can move this function inside here, and this is going to be an upper bound. Now, we're going to do logs. Logs are convex the other way around. So then I just have the different behavior here. If I have a log of an integral, I can move the log inside, and this is now a lower bound on that. Yeah? Cool. This is called Jensen's inequality. And to me, this is really, really important. Because to me, I don't like when people derive variational base out of we're minimizing a KL divergence. To me, it's not. To me, it's we are making use of the Jensen's inequality by picking, as a very good discussion the other day, we're picking the log as the convex function that we want to use to get this bound. Right? That, to me, is very, very important. And if we do that, the KL divergence appears, as you'll see now. Cool? So if we go back to this, now I'm going to move the log inside here. I'm going to move the log inside and get the lower bound. The way I move it inside is this. So qx, one inside the log and one outside. It's a lower bound. Now, this p of y, I can take out of the log, and I get qx dx log p of y. This is a distribution, so yes?
How come 1q is outside of the log?
I choose to do that to get to, because otherwise, if I move them, I need to somehow separate them, because otherwise it doesn't do anything, right? So this is just the way I do, but that's still going to be a lower bound. Yeah? So if I can move p of y out. This is a distribution. This integrates to 1. So this here just becomes log p of y. And this thing here is now the negative KL divergence, right? So it's qx, px given y qx, right? You saw it yesterday with qx up there. So you do the negative with the log and you get a -1 outside. So, cool. What I actually have now is that I got log p of y, log p of y. This is apparently smaller than that. Well, fine. That's true. Because this is always positive and it's a negative thing there. So I know this here is only ever going to be 0, this equation here, if these two are equal to each other. So that means if these are equal, this is tight. Log p of y is equal to log p of y. Right? Cool? Great. So this, to me, is why we use this term. Right? Because we do the Jensen inequality with the log. Right? Yeah? Cool? So now, it also says this interesting thing. When I introduced q of x, I didn't say anything about q of x having anything to do with the posterior distribution. But because this is now a measurement, it says if this bound is tight, q of x is equal to the posterior. Great. So that's something that appears from this now. So what I want to do, therefore, is to minimize this, find a q that minimizes this, which means, because of this thing, that this distribution is an approximation to the posterior distribution. Yeah? Cool. So now we're going to flip this on its head and say, great, well, that didn't do much. Now I'm going to do the other way. So now I'm going to say, well, great. I've now hopefully justified that this is the object that I should minimize. So let's now figure out what that is. Because I still can't minimize this. Reason why I can't minimize this, I don't know what that is. If I had that, great. Job done, right? I haven't done anything. So what I do, I write it up first. Now, we are going to do exactly what we did to this term, but the other way around. So what I'm going to do is that I'm going to take out log p of y. So I'm going to write this as the joint. I'm going to do, well, base rule, I guess, or the product rule. So I get the joint distribution here, and I got log p of y out. Now, I can split this term and I got the entropy of Q of x, and I got the expectation over the log joint distribution over Q of x. This is what I have, and I got KL there. This term is clearly intractable because I don't know this. This term here is also intractable. I don't know what it is, right? Because I require this term to reach this term. Cool? So now I can flip all this around, and I just moved every element around, which is why I have log P of y is equal to the KL divergence, which is always positive, plus this thing. And this is why we call this the evidence lower bound. This is the evidence, this is always positive, so this here is a lower bound on the evidence. Yeah? So now I can maximize this and thereby implicitly minimizing this. Yeah? And that's variational base. I hope that was still useful to see that, because I think it's very important to know where these assumptions come from. Often it's just explained, cool, we throw this as an optimization problem. Yeah? Excellent. So now we write this just as this lower bound. We're going to call this L. So the cool thing now, to summarize, if we maximize the elbow, we find an approximate posterior. We get an approximation to the marginal likelihood. We should be a bit scary about that because we don't know how tight this bound is. Now, what we are definitely doing is we're maximizing this. To me, that's learning. And we're finding this, and that's prediction. Finding an approximation to that. So we're doing everything that we want to do as machine learners. So another way of seeing this graphically is that I have this, I've specified this conditional distribution, how x generates y. What I want is to get P of y. Another way of getting P of y is if I had the posterior, I can do Bayes' rule like this. I can either compute this horrible integral that I said is intractable. The other way is to do, this is normally how you see Bayes' rule, right? You see this one up here, right? If I flip these two objects, I avoid the integral, but that means I have to compute this, which I can't compute. So that's just how these two objects are related. So what we're saying is, I can't do this, but I'm going to try and do this. Because if I do this, I have these, right? So what we're doing is that we're approximating, we're effectively cutting the dependency between x and y and giving a parameter to q that should now encapsulate all the information that y has, so I don't need that dependency. That's the ideal scenario. Yeah? Cool. Are we all like, yes? Yeah? Good. Perfect. Everyone should listen to Talking Machines. Ryan Adams, who was the previous host, Season 2, Episode 5, they talked about variational base, and he had this very nice American way of saying why we should do this. So he said, well, if you can't formulate the joint distribution, that's the object that you need. If you can't formulate the joint distribution of your model, well, you're not finished with your modeling, so there's no point of starting to think about doing inference, right? Like, you need to think about other stuff first. So joint distribution, clearly we can formulate that. And secondly, we're taking the expectation of a log. Most distributions that we work with will always be in the exponential family. The log of an exponential is generally easier than the exponential in itself. Cool? So that makes this easier to do than the general stuff. And then the last bit is that you're allowed to choose the distribution that you take the expectation over. Q, the one outside the integral, you can choose, right? Of course, if you choose it really bad, your bound's going to be terrible, but you can still choose it so that you can compute it. Which means, in worst case, you should always be able to do this. Right? You should be. Okay, so now, great. Let's just do this with GPs. It should just be dead straightforward. So now, what I have, let's say I want to integrate out x and f. So what I have here is that I write this lower bound in terms of x. So it's just this KL divergence, right? Or part of the lower bound. So this is what I need to compute. Cool. So let's expand this term. So I expand this term into my likelihood, my GP prior, and my prior over x. So I get this. Great. Easy peasy. We haven't done anything. Now I can take this Q of x, P of x out. this I should be able to compute. This is like the KL divergence between my approximate posterior and my prior. And then I'm left with this thing here. So I'm now going to say this I can compute, so I'm going to remove this. Otherwise, the equations are going to be too long. So remove that stuff. And I'm left with this L term. This is what we're going to look at, this object. So the problem is, I haven't really made the problem any easier at all, actually. Because I'm still left with this super annoying thing of x going through a nonlinearity going through here. Like this integral I still can't compute, right? So I haven't done anything. It's like still intractable. So now, and this is what James said, cool, let's put a Q that's a GP. Great, right? Dunk, that's it. So now I'm going to explain what assumption that implies, because it implies, to me, a very interesting assumption. So the idea we're going to use is this idea of sparse approximations. So what we're going to say, now I have x and y pairs. These x corresponds to y, and there's a GP that should relate them. What I'm going to do is that I'm going to say, well, I'm going to draw some new samples from this GP. I'm going to take some z's. This is part of the confusingness of this paper with the notation. I try to be consistent with the paper, which means now all the letters mean something else. Z is in X, U is in F, okay? These are additional samples from this process. So I'm just going to say I got this process, data here, something relating to them. I'm going to take some other points in X that I don't know, and they correspond to some other points here that I don't know either, right? But I'm just evaluating it at a new set of points. Cool? What I can do then, and this is really cute, now we're going to exploit this thing that you can do base rule in closed form. So what I'm going to do is that I'm going to say the joint distribution here, clearly, they're from the same prior. The GP definition was that everything is jointly Gaussian. So F and U are jointly Gaussian, evaluated at X and Z. Fine, right? Now I can write that as F given U, and this just here, the prior U given Z, right? That's absolutely fine. One thing I recommend everyone that's starting with Gaussian processes, derive the Gaussian identities by hand once. It's really, really useful. Derive exactly how this appears. You'll use Schur complements for the first time since you did linear algebra. It's really nice. So that here becomes just this, okay? So now I got, if you want, this is also how you do predictions, right? This object here was our predictive distribution. Cool? Now I'm going to put this into my model. So I've added U and Z here. So I just add this into my model. Blah, blah, blah. Nothing really happens. Now, what we're going to do is we're going to treat that to be Z, U and Z, not as random variables, but as variational parameters. So this is, I'm going to use these parameters as the thing that parameterizes my variational distribution. It'll become clearer in a little bit. So now, what we want is that I need a QU, a QF, and a QX. These are my approximations that I need. Clearly, we know that this should approximate U given everything, F given everything, and X should be this. Cool? So now, what we're going to do, this is a very strong assumption, and this is the assumption that we use. We are going to assume that we can find U's that completely represents F. What this means is that U is sufficient statistics of F. So what this means is that Q of F is really approximating this posterior. What I'm going to say now is Y here is just a noisy version of F, right, if you want. And if U completely parameterizes F, Y provides me with no additional information to represent F, right? So if this is true, I can cut Y and say that this here is now that. Yeah? Does that make sense? So this now is the posterior over f, having observed y and everything else, right? Okay? So now that has a really, really interesting thing. So now let's come back to this. I write this up. I have q of f here. Remember, we moved q of x out in the beginning to this KL divergence. That's why it doesn't appear here. Donc, now, likelihood, I have now my conditional distribution, and I got my prior, q of f, q of u. Now, I'm going to put in this assumption that this here was actually this distribution. It had no dependency on y. Yeah? If I put that in, you're going to see that this thing here, which is my joint distribution factorized, that q of f is exactly that object there, right? And now I can cancel them, right? Does this make sense at all? You probably have to look at the derivation. There's a lot of math here. But my assumption is that I said I have this posterior, but I can drop y. I can drop y. Now this just becomes a conditional Gaussian distribution. And if that is true, I can write my joint distribution where this conditional Gaussian is a factor, and now I can cancel them. And if I can cancel them, so I cancel these two, I've done something really, really remarkable. Because what I've done now is that I've separated x here from y. So now I no longer need to propagate the uncertainty from x down to y, because I'm saying all that information is encapsulated in u. Right? My sparse points should have all the information that I need, so I no longer need to do this integration the whole way. It's like putting up a wall. Something needs to go from here to here, and this one can't communicate with this one, so I put a wall here and say everyone needs to communicate through this thing. And now I'm going to optimize this thing, so that that communication is ideally perfect. That's at least my objective function. Okay. So this is what it reduces to. So now you have an expectation over all these q's, over this term. This is hopefully tractable. Then I have some KL divergence. And this is really doable. If you want to read about this, I really recommend Andreas Damiano's thesis. It's really, really well written and explains a lot of these things in much more detail than I did. It's not as tricky. It's just a lot of math. And I think the key thing to get is that now you know the assumption that we made in order to be allowed to use a GP as approximation. Right? It's a very, very, very specific assumption. Right? And that's why this was so hard to do. And it's one, again, when you see the intuition, you think, oh, that kind of makes sense. And that's always the brilliant work, right? Cool. So what this now allows us to, yes?
Does the assumption mean that u might be infinite?
So very good. So clearly, if u has the same expressive power, you put enough u's, the same as the number of data, ideally they should just find the data points, right? That's going to be exactly the same thing. So what you want, right, is also, this was actually how it was motivated initially, is that you want to do this in order to make a more efficient computation. And you do that by having a small number of u's. And you saw in the lab yesterday, when you picked, try and reduce u's, like use tiny number of inducing points, and you're going to see what it does, right? And now you know what it's really trying to do. It's really trying to say, can I be sufficient statistics for everything, right? So I don't need y, right? Yeah? Cool. So the coolest thing now, because I was supposed to talk about unsupervised learning, which we'll get to, is that if I come back to this, this is the really cool thing. So now we learned how to integrate out x, so I can now make assumptions about x. The cool thing is, how hard is this to do? Well, look at where x appears. X appears here as my approximation, But in the bound, the thing that I'm optimizing, it only appears in this KL divergence. That's the only term where P of X appears. This is like, wow, fantastic. Now I can chuck whatever I want in here, and happy, happy, joy, joy, off we go. Right? This is really, really nice. So what we're going to talk about now is exactly what I said. Unsupervised learning, we've kind of been convinced by that the GP does something sensible. We need P of X. Cool. Now we know how to deal with P of X. Surprisingly, we realize it's really easy. It's just in this KL divergence. Great. What kind of P of X's can we do? So that's what I'm going to talk about now, and it's going to go a little bit quicker. When are you going to throw me out? 1:30. Okay, I'm doing my best. If you buy me beer, I talk forever. So if you want to ask questions, just like invite me to the pub. So the easiest thing, which we already talked about, to use as a prior, is just to think, I want the latent space to be small. So let's put a Gaussian on it. The nice thing with the Gaussian, or any distribution, I guess, is that, let's say this, if I want to learn the dimensionality of X, if I put a 10-dimensional Gaussian, it needs to spread its mass over a bigger volume. So if it allows to make a 10-dimensional Gaussian 5-dimensional, it's happier, right? Every space point in that space is happier because there's less volume to spread. So every place becomes more probable. Great. So even though I never ever want to learn anything that looks Gaussian, this here is really useful because it has this effect, shed loads of distributions, everyone is going to have this, right? That it's going to reduce, it wants to reduce the number of dimensions that you have. So the easiest thing you can do with this is that you can place a kernel, you can alter your GP prior by adding a parameter. So if this is your squared exponentiated quadratic, is Neil here? No. Squared exponential kernel, what you can add is you can add a variable which is a scalar per dimension of your input. If this here now goes to 0, well, that dimension is gone, right? It doesn't use it in the regression. You can add this to any of your examples by, when you create your kernel, you add ARD true. This is referred to as automatic relevance determination. It might be referred to that correctly when you do latent variable model. When you do regression, not so much. It's actually much more complicated than one thinks, but it kind of often has this effect that it turns off. If you're interested in this, Aki Vitari's PhD thesis explains that it's actually not as simple as one thinks. It has some rather interesting effects. Okay, so that's one thing. The next thing is now my theorem, my second one, and this doesn't come with a joke, is this change of variable theorem. We use it every day. Let's forget about the text and we come back to that. It just works like this, right? This is how all our computers work. If I have a beta distribution, I want to sample from it. What do? Well, I compute the CDF of that. Then I flip this thing around, blonk, and now I can sample from a uniform distribution, push it through that function, and all samples are going to be distributed as a beta, right? That's how our computers sample stuff, right? As long as you can sample uniform numbers and you can compute the CDF, you can sample from anything, right? That's exactly how it works. So now, this is exactly what this theorem says. So if I have a distribution, x, that I know of, and then I have a mapping from y to x, psi, now I can get the distribution over y here. I can get a distribution over y by taking p of x, I sample from p of x, I take the y's, push them through the mappings, I get x, I evaluate the distribution here, and then I take this, in the multi-dimensional case, it's a determinant of the Jacobian, but think about it, is you just multiply this with the gradient of this function, the absolute value of the gradient. So what this means, another way of thinking about this, is that if your function has a very, very high gradient, it's going to stretch the uniform distribution, right? In this case, if you think of the uniform here, Here it stretches it, the gradient falls down, it compresses the distribution. So here it takes a uniform and like, and it gets a beta. Yeah? So now we can use this, because what we can do is we can use this by take these mappings and we can warp things to say, for example, non-Gaussian things. Yeah, that's really cool. So, yeah, there it came back. And there was a really early paper on this called Warped Gaussian Processes by Ed Snelson, who kind of disappeared. I haven't seen him for forever. He did really excellent work on this, and Zubin, where they basically said, we're going to take a monotonic function. I have some data here which is non-Gaussian. It's 2004, that's why the plot looks like 1904. So you have this data which has a really non-Gaussian likelihood like this. It's non-stationary, and what they've done is that they said, cool, I'm going to take a variable here. That's y, my data. Then I'm going to get another variable up here. And then I'm going to model this variable, and then I'm going to find a mapping that makes this variable Gaussian. Now I can model this with the Gaussian process, and plop, it goes. So you can see this by this slice here. That's the distribution over this point. Very non-Gaussian, where this is a Gaussian distribution. Cool. So now we can do non-Gaussian data. Of course, the only thing you've turned this into, how do I learn the function that actually does this warping? Well, we know how to learn functions, don't we? Exactly. So why not make this function a GP? Right? Cool. So now you have a GP and a GP, or a GP and a GP and a GP and a GP. And now we can be really cool, right? Now we can hang with the cool kids because we can now use the word deep. Fantastic. So this is what's called deep Gaussian processes. So now you warp and keep warping and keep warping and keep warping. You do this variational bound on this, which is going to have a bound in 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 a bound. And that's great, right? That's all we should do. We can just end, because this we know is black box, and the no free lunch theorem no longer holds as long as you're deep. So now I thought I should have a rant. So the thing is, mathematicians have looked at this. Can we, one, agree on stopping calling things deep and call them composite, because that's what mathematicians say, composite functions. This is the notation of writing a composite function, please. Okay. Now we have about 400 years of science to rely on. There's lots of interesting limit proofs on these, for example. So one thing is we're doing stochastic stuff, so we're talking about distributions. So let's just do a funny example. So this is now my function that warps a uniform distribution. Bang. So I did this. Cool. I warp that. I end up with this. Great. So now I'm going to make an example and say, fantastic. Let's now be realistic and say that these are two classes, and we're doing some classification. This is the distribution of the data. To be, again, with the cool kids, let's make this realistic. So this is cats and this is dogs. You know, we're doing important things. So now we want to classify these. We want to separate these two things. Great. So we keep learning these warpings, right? So now I'm going to take this warping function. Now I do blah, blah, blah. I'm ending up with this. Fantastic. Now my classifier can drive a bus through this. Lovely. Actually, I lied to you, because that's not how the warping function actually looks like. If you push this through that function, it actually looks like this. Right? It's two delta functions. So now we've done the best thing in the whole world. We've mapped the whole continuous uniform distribution to 2 points. And my task was to classify two things, right? Great. Realign to 2 points. Lovely. However, this has some really interesting things with it. So the way I like to describe it is through this. So David Mackay had this in his dissertation. Has everyone seen this plot, right? Yeah? So the idea, the idea is this. Why we Bayesians say that we automatically don't have to deal with overfitting, right? We're automatically regularized. Occam's razor is automatically implemented. We say that because if I optimize the marginal likelihood, what's happening is if this model here, this is the data set is somehow ordered. if my model places probability mass here, then it explains all these things. If my model places probability mass here, it explains all these things. The less it explains, the more probable my data is going to be, right? Because it just has to explain less. Yeah? So if I pick the model that best fits it, that has the highest thing, I will pick the right complexity. I won't be over complicated or representing something too big and not too small. The problem here becomes when you do composite model, because composite models works on this space. So what a composite function is doing is that it's reshuffling this space with all these crazy functions so that all your data lies here. And now it can place a model which is awesomely probable because it doesn't have to model anything except for exactly your data. And this is why deep learning requires insane amounts of data, right? Because you need so many sample points to avoid it, to shuffle it down so that a trivial solution can deal with it, right? So, and we have exactly the same problem in GPs. It's a problem with composite functions. It's not a problem with neural networks or whatever you want. So another way of seeing this is seeing that if you composite a function, the image of a function is all the points that the function can map to. If you composite a function, the image can only ever shrink. You can ever represent less points. So the more depth you add, the less representative power you have. So people say they have more parameters. No, you don't. Like you have less representative power the more depth you add. The kernel, which is everything that's projected away, that maps to the same point, increases with composition. This you can see here. Now, remember that theorem I had with the derivative. What are we using as activation functions? ReLU. What's the derivative of a ReLU here? 0. It means all that data, that input space is gone. It does no longer exist. And the scary thing with that is these things, right? Which is exactly what's happening. If you move a point a tiny bit, it doesn't jump smoothly. It jumps massively, completely without control. And that's why we see these things. Oh, I think all these are classified correctly, and these are all classified as cats or something like this. And this is the delta between them. So you have to be really careful with this, with GPs and with other models. You have to be really, really careful when you do deep models. And the only successful things I've done with them is when I've had functions which are composite and I can specify insanely constrained priors. Really, really constrained priors that have very, very little. I know so much about how the function is composited. Otherwise, it's going to do weird stuff. Oh my goodness grace. Okay, so the last thing that I wanted to tell you about, we'll try to get through with this, is about not going deep. So not saying, I'm going to put lots of funky structure on the function by changing p of x, by basically adding lots of more GPs that warps it, so I get a prior that's some warped crazy things that I can't express. What I'm going to now explain is when we add other types of structures, but in a flat model. So, fundamental concept in machine learning is explaining a way, right? When we add noise to something, what we're really saying is this in unsupervised learning. I have some data y. I say that this has been added Gaussian noise. Can you explain away the Gaussian noise for me so that I can explain the signal? That's exactly what we're saying. If you compare the variance of your GP with if you have a white noise and an RBF kernel, if you divide the variance of those two, that's your signal to noise ratio. So this is explaining away, right? Okay? So sometimes I have models or data where what I really want to do is that I want to explain a concept as factors of something else, right? This is a person, and I really want to explain it as height, weight, and nationality or something, right? How do I know, how do I get the model to keep this structure, right? This is interesting. How do I specify that it does that? So it doesn't do like, well, this is height, weight, and this is something else, that he mixes this. This is what's called factor analysis, which people in psychology do a lot. So one way of providing supervision for this we call alignments. And this is interesting. So the way you can do this, do an example of this. So say that I have, this is a data set called a coil data set, where you got images that have been sitting on a turntable. So you have images, and you know exactly what angle they are portrayed in. Now what I'm going to do, I want to learn an unsupervised latent space that can represent these images. But what I really want is that I want to separate the image from the position it was taken from, right? So if I just stack the data together, the model will never ever, it's really hard to provide the supervision for it to separate these two things together. But what we can do is align the data. So we represent it as two data sets. So what I'm going to do is I'm going to work with ducks and cats. So I'm going to take all the ducks and align them with the cats which have the same camera position, right? Now, if you think of having a Gaussian prior on a latent space, so it wants to find the smallest representation it can. The smallest representation of this would be this. What it would have to do is say, well, you know what? There's no duck information here. So if I start trying to put duck information, that's a part of generating this, I'm getting penalized, right? Because there's no duck here. And the same thing with cats. So in a way, this information is private to what I will call views of the same problem. There are two views of the same data. But the rotation, if I represent the rotation in a shared way, that is shared between the duck and the cat. So if I give the model the data like this, in an ideal world, it should be able to separate out these factors, right? And that type of supervision I can potentially give. You can flip the example of saying, if I give the same class of image, but I randomly do the rotation, it can't share the rotation between the views, but it can share this. So you should get this factorization of the data. Yeah? So I have no idea what I did there. Oh, I went backwards. Good. Another thing is you could say this. You can say that one view is the class of the object. You want to do classification. And the rest of the view are the images. Now there's shed loads of things in the word cat, which in the image is like, it has nothing to do with cat. That black pixel, for example. And there's lots of additional information here which is not useful for cat. So in this case, the model would have to separate the information that's relevant for classification in these images from the information that's irrelevant to the information, if you want to classify, that's ambiguous. This image, I can't separate it. Like, I can't say what this is, so therefore I have to have something extra to the class here that can represent this. So now think about this as explaining away. I have this data set, and I'm explaining away the irrelevant information so that I can do classification with the relevant, and I can say, I can decide it up till this, but no more. So you can do this very, very easily. So what you do, we've already said it. You just factorize your data, split it in two views. You place one latent space, but each latent space is generated by two different GPs. They now have two different ARD kernels on each other. So that parameter that said, should I use this dimension of X or not? If both of these uses the same dimension, it's shared. If it's 0 in one and non-zero in the other, it's private to that view. It just works. It's really cool. And it really, really simply works. We're trying at the moment on a really cool data set with this, trying to do, when you cultivate stem cells, you want to reduce the number of mutations in the stem cells. So now you want to figure out, you have mutations on one side, what environments, what treatments to the stem cell correlate, are important for the mutation, right? That's exactly that. I can do lots of things which has nothing to do with the mutation. Cool, they're going to be private to that side. But if there's something that's joint between them, it's shared, and therefore the biologists are interested in it. Yeah? Cool. Now, it's actually a funny story about this. Andreas, Damiano, and me and Neil did this paper, 2012 or something. 2016, we tried to write a journal paper, which is still not submitted properly. The reviews of this journal paper pointed out another paper from 1958 that did exactly the same thing. However, in 1958, there's a beautiful quote in the paper. It's linear and hasn't does GPs and stuff, so it has some value. But it pointed out in the paper, there's a quote saying, this algorithm is so complicated that it will require an electronic computer in order to solve, which I thought was very, very cute. So that's called inter-battery factor analysis. I had no idea about it. Now, I'm going to rush through some very recent examples. So another thing, you can now question yourself, how do I know which should be a view? How do I know how I should group things? Where am I interested to find in these shared and non-shared factors? Well, there's another stochastic process called the Dirichlet process. And a Dirichlet process is a stochastic process over partitions. So in very recent work, it just came up on arXiv a couple of months ago, we do exactly these models, but where we have a Dirichlet process that selects the partitionings. And what you can get from this is now you have each dimension of the data is a view. And what you get out in the end is this matrix where this is a latent dimension, these are the ARD weights, and these are the observed dimensions. So this says I only need 4 dimensions to represent this data, and dimension, whatever this is, uses this and this, but not this. So now I can see this dimension here, which might be something interesting, shares this latent dimension with this one. And this is quite an interesting factorization of a problem. And now, to tire people, I'm not sure if I'm going to be able to talk about that. I am going to say one very quick thing. So another thing that you can do if you're interested in constraining these latent spaces, people are very excited about something called amortized inference nowadays. If you look back in history, there's a paper called Neuroscale from 1992 that did these things. And what you do is if you do unsupervised learning, you represent your data, your latent space, as a function of your data. And now, rather than learning the latent representation explicitly, you learn it implicitly by optimizing this function. In GPs, they're often being called back constraints. You can do these, and then I think Zhenwen and the people here had a paper, Zhenwen and Andreas and Javier and Neil had a paper called Variationally Autoencoded Deep Gaussian Processes, which is exploiting this in a deep Gaussian process. It's really, really simple. You're just making a change of variables. So, in summary, now I'm going to end. What did I try to convey? Well, to begin with, unsupervised learning is very, very hard. People say this is the toughest thing that we can do next to reinforcement learning. That's absolutely not true. It's really, really easy. Unsupervised learning is the easiest thing because no one can tell you what's right or wrong. You can only be right or wrong. This is true for every machine learning thing. You can only ever make an argument that relates to your assumptions. You can say, if I assume this, this makes sense, right? Then you can be wrong, but that's inductive reasoning. You cannot say that you're right or wrong, right? So therefore, you always need to state your assumptions very clearly. So unsupervised learning becomes tricky when we want to make interesting assumptions, and it becomes tricky in terms of inference. So yes, relevant assumptions and strong assumptions. And I hope now you see the cool thing about GPs is that they give you this really powerful handle to input assumptions. That's what machine learning is. Machine learning is about formulating mathematical tools to allow us to place our beliefs on data. That's all it is about. And GPs is very natural to reason about functions. Parameters makes no sense to me, but give me a covariance function and I can spend all night to talk about how I think this works, right? And I hope you will start seeing that as well. So, great, I'm saying everything before I click. Okay, so then my rant, just think about this with composite functions. Please go and read some math about it, because it's just very scary when we just forget about 400 years of science. It's not what I said with this image kernel thing. That's like, it makes sense to everyone, right? But we need to be a bit careful about this. So we need to think about this. So the thing what they really, really do is they're a way of modeling less things. And when we have very big data sets, so if you've got 10,000 images, for example, to model, well, you have no concept of what 10,000 images are. So if I show some samples in a paper by drawing a random image from my training data set, even me as the one who did that thing have no idea if that came from the training data set or not. I can't memorize 10,000 images. It's a really good blog post on off-convex where they show that the sample diversity of a GAN is smaller than the training set data set used to train them, right? And this is if you went to the NIPS craze last year, or if you potentially managed to get a ticket last year, that's what 50% of the community seems to be talking about. So think about this. Cool? So, blah, 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 blah. And that is the end of me, and I finished with 3 minutes. So if anyone has any questions, please go ahead. The steelworks? Yeah. The steelwork, it's really interesting. So no. The answer to the steelwork is this. It's refraction, right? So if you got water is generally it's called something, this test, when people do this, and they measure this all across the planet. The interesting thing is, where do you find something that's really, really flat and really, really long? Well, water, right? Great. Now, if you look over water, you got refraction, right? Because you got two different substances, you often have two different temperatures, so actually the light is going to refract over it and actually bend, right? That's exactly what's happening. It's a really interesting thing. So it's like I like flat Earth people. I get interested by them. There was a flat Earth conference in Birmingham not long ago. I couldn't go, but it's amazing what people do. But the key thing is we laugh about this. But machine learning wise, this is exactly how our algorithms work, right? The data that I had exactly, my theory of a flat Earth exactly explains my data. And then we use assumptions. We say Occam's razor, right? Oh, great, this is the simplest assumption. Well, what's the simplest assumption here? Well, my simplest assumption is the Earth is flat, I can see it, or my whole refraction thing, right? Oh, most people will probably say, well, at least if I meet a 5-year-old, they would say flat Earth. Great, right? It's much easier. So even the concept of what's easy requires assumptions, right? You've made an assumption by saying, well, this is an easy explanation. If I was, religious in one way or the other, I am more prone to a certain explanation of something. So it's super important to not forget this, right? And if you learn something, if you get something out, there is an assumption there. But the tricky thing is, and Noam Chomsky talks about this, what's called the inductivist fallacy. And he says the tricky thing is when we solve things and then try and come up with what assumption that was in order to solve it. Now we've broken the scientific principle completely, right? And that's really, really scary. And I think we actually see this a lot, right? Cool.
Yeah, so any questions that I'd like on the
Yeah, so this animation with this this letter and then the latent space.
Yeah.
Worked nicely. And as I understand, was maximum likelihood.
Yeah.
And we continued on
Yeah.
like a long path of variational phase.
Yeah.
So my question, maybe as an engineer,
Yeah.
is more like, what did we gain?
I know, and do you know what? The most annoying thing in this case, right, is that he had all the tools to do it, and he runs variational based on it, but the issue with that is that that worked worse. And that was a SIGGRAPH paper where the only thing you care about is results. So the interesting thing here, now we should come back to the no free lunch. What that means is that Neil, who's a very, very clever man, Neil Campbell, who did this work, is that he could place his assumptions better on a maximum likelihood. For him, it was clearer to say, you know what, if I initialize it like this, I'm going to be close to that local minima that I'm really looking for. That allowed him to place better assumptions to get the solution that he wanted, right? Then say, cool, I'm going to formulate this as a distribution, marginalize it out, dunk, to get that result, right? It's all about assumption. What I'm saying with maximum likelihood, is that those assumptions are, for me, it's very, very hard to make those assumptions on a maximum likelihood. There's, of course, certain things you can't do, which so say, for example, dimensionality. If I increase the dimension of the latent space, maximum likelihood just says it's better, right? So that means you need to decide what dimensionality it has. Cool, if you know that, he knew he wanted to make a web page, therefore it has to be 2. Right? Great. That's his assumption comes in like straight away, super easy to incorporate in that framework. Yeah? Cool. But and this is often true, right? This is often true. This is the magic. I think Neil Lawrence says this often. Like, you know, there's certain people like Jeff Hinton who's just insanely bright, and they'll be like, yeah, we should do this. And it's correct. It works, right? It's awesome, all the stuff he does. For simpler people, we have to use math, right? and that is not saying anything bad about him, right? That's the best thing because you've internalized these processes. It's awesome, right? It's really, really great. Sadly, like, I'm not Jeff Hinton, certainly not, and maybe some of you are, right? But it's just about how can you formulate your assumptions. Then the interesting things comes in science. Can you communicate that? I bet you Neil Campbell, who did that, has a hard time actually communicating the assumptions that he did, right? But if I formulated a prior, I could say, look at this, right? I believe this is student T, I believe do with this parameter, blah. That's really communicatable, right? Now you can understand it too and go off and do really cool stuff. Yep. So there's the... Thanks. Yeah.
And you said that we are more affected. We explain a smaller range of data.
Yeah.
Is it does it affect also the Bayesian framework?
Yeah, absolutely.
So even if we marginalize out the latent variables,
yeah,
we are more affected by overfitting when we compose functions. For example, when we are using the Gaussian process.
Yes, absolutely. So let me see if I added this. This is my long appendix of crazy things. Let me see if I added this. Oh, I didn't get to talk to my cricket players. Let me see if I had. No, I didn't add this. Blimey. So there's a classic result in deep GPs, which everyone argues if it's a good or a bad result. Where people try and learn a step function. So you've got data like this here. Right? Cool. Now we know this is not even differentiable, it's horrible. But I know GPs, so I'm going to put a deep GP with an RBF kernel on. So I'm trying to learn a non-differentiable function with an infinitely differentiable assumption. Great, whoa, you're in some sense, okay. So what happens when you put this through a couple of layers? Now you get a function that perfectly does this, okay, nearly perfectly. It's not strange, right? Because what you do, each layer is going to put something like this. Now you stretch and stretch and stretch this space. That's fine, right? That's cool. But the interesting thing is what's happening here. Because each function is going to look like, that or something. The gradient here is flatter and flatter and eventually becomes 0. So if you plot the uncertainty of this, the uncertainty is like nail on, tiny, tiny, but the really scary thing, it's tiny here as well. It's exactly the same because this part of the input space doesn't exist in the model, right? But when we plot this model, we plot it over the original input space, right? That's what you have to do. That's the interesting thing that we want to relate. So to me, this makes absolutely no sense whatsoever. I've given a prior that says the further you are away from the data that you've seen, the more uncertain you should be. That's a stationary covariance. And you give me this, right? Something's very, very odd here. So there are ways, not sure if I'm allowed, hopefully, after AI stats, you should hopefully see a paper that deals with this. But it is really, really, uncertainty does really weird things in compositions. I can show you another thing. Please, stop me, throw me out when yeah. So another thing which is really interesting with uncertainty, when you propagate it, so what happens? Let's do this. Take an identity function. It's a very skewed image here. Put some uncertainty around it. It's tiny. Now, I push this through a sinusoidal, right? This is the uncertainty that comes on this item. The identity function just moves this space like this, right? Now I add some uncertainty to the sinusoidal. Now these two uncertainties adds up to this. Okay, there's a slight difference in scale here. This is an identity function here over. But now comes the interesting thing. If I sample from this, all samples are going to look like really nice sine waves, very unnoisy, that I just shifted along here. Because the biggest noise comes from here. But if you do what Nicolas talked about on the first day, I now want to put a point here and see how valid that is under my function here. Well, it's going to say, well, that's reasonably certain. Because the interesting thing is now you correlated everything together, but you're evaluating according to X. Right? Do you see what I mean? Like every sample will be a really nice sinusoidal, but this uncertainty to me makes no sense whatsoever. Right? It doesn't. So the way I think about it, now I'm saying more than I should, possibly my student will hit me, but the way I think about it is that we need to decompose uncertainty in compositions make no sense. You need to think about uncertainty in two ways. You need to think about the function as a composition, but you need to make another prior assumption about the uncertainty. Because I hope you agree with me that this is really hard to reason about. It's really, really hard to reason about. And it becomes bland very, very quickly. That's why it's so hard to do reinforcement learning with GPs. You push uncertainty a couple of levels, everything's probable. Right? This is and we need to rethink that. Right?
Yes, we probably want coffee. Cool. Thanks very much. Yeah.
Thank you.